Hello and welcome to today's episodes of Disaster Discussions. Welcome to our podcast. We're here at the IBHS studios and we have a new face with us here today. We have our research scientist, Merhi, joining us here today, and we're actually going to be talking a little bit about the tropics. We are in November as we are airing this episode. It's the last month of hurricane season, and so we're going to get into some of the details of our deployment that we had on Hurricane Idalia. Talk a little bit about the season recap and get into a little bit of the science behind some of those observations and why we take them. So thanks so much for joining us here today. And Ali, thank you for joining us here today. This is actually your first visit with us here on the podcast.
Yeah, it's been a while, and I'm really happy to be here. Thank you for having this chance to chat.
Yeah, it's been great. So, we've been here over a year now. It's hard to believe that we've been doing these podcast episodes for a year. And when we do these, we like to highlight our own scientists as well and show you a little bit of the inside workings of our research facility and some of the data collections that we go through. And Ali, today, I know we're going to talk about Idalia specifically, but there's some other deployments that you've also been out on recently with our HAIL team. You've heard us kind of reference these in past episodes where we go out and do these disaster investigations, but in this case, we actually went out before the storm. So we're going to talk a little bit about that. So first of all, let's share a little bit with our viewers about you, kind of like some of your early career and how you came to be at IBHS. And I will ask one question to begin with, pointed. What got you interested in wind engineering?
It all started with my interest in buildings and construction. So I remember when I was a kid, my father used to drive me back from school, and there were a lot of construction sites, and you see a lot of people getting involved, and that was in the early 90s, so prefabrication was not really the mainstream. So a lot of people coming together to achieve a building, and then watching cartoon or whatnot. I remember like Disney's Hercules, for example. A lot of disasters, earthquake, wildfire, wind, and you see these buildings getting torn so easily. And in the background you have this issue, a lot of people making this monument or anything, and then suddenly just by peril, they just disappear, right? So that put me on the path towards civil engineering, and particularly bridges. And as I was studying those at university, I noticed that wind is a particular issue, especially as construction and buildings are evolving. We're going taller in buildings and longer in bridges spans. And we shift by doing that from earthquakes being the main driver of the failure to wind.
Yeah.
And looking at the complexity of that, actually, that sparked let's say the scientific interest. But seeing the impact of that, when you have a hurricane impacting states and the loss it leaves behind, it gives you also the seriousness of the impact on society, on people. So all of that kind of gave me a sense of curiosity on how do we solve this. We have come so far as society and science. So yeah, that's how it all sparked, basically. A lot of factors from here and there, but it was all fueled by the way, like childhood and cartoon. I remember Dorothy Gale from Wizard of Oz in Kansas.
Yes, I know, yeah. That's inspiration for a couple of other people here at the lab too,
Yeah, exactly. So, all of that just sparked the curiosity on solving these issues from a scientific perspective. And that's how it all started.
Yeah, that's great. I mean, I think a lot of us probably have that moment in childhood where it's just kind of like the light bulb went off. Some people experienced a weather event, and so we always like to ask people about their stories and kind of see like what their perspective was. It's just interesting to see how people's motivations kind of evolve as they grow up and that kind of thing. So thanks for sharing that with us. So we talked a little bit about how you kind of got interested into wind engineering. Let's talk a little bit about your academic background, because your roots go all the way back to Genoa, Italy, I believe. So just kind of want to talk a little bit about your academic background and how you got to be here at IBHS and found our cool facility.
So as I was saying, because of all these perils, I chose to go and study in Italy, and particularly University of Genova, because they had this good program in civil engineering. And it all started with the interest in earthquakes, to be frank, because in my childhood, I was in Beirut, in Lebanon, and there were a couple of earthquakes I remember in the building I was living, and you feel the building shaking. So I started there, and as I was getting closer to the end of my bachelor's degrees in Genova, I noticed how, like slender buildings tend to be failing due to wind more, which was shocking to me. But really, like that thread that I caught on just pushed me towards going, to the masters, and then just what happens. So like, sometimes you conclude something with a question, and that's what happened. I ended my bachelor's with that question. Why do buildings fail due to wind more than earthquakes in these particular cases? So following that thread, I went into, some kind of structural dynamics, how, like when you have the way that the perils act on a building, like during an earthquake or during wind, you have some dynamic interaction. It's not just a brute force that acts. So that pushed me towards understanding more like the structural dynamics. And I ended up with more threads. So, like you end up with seeing one equation that, for example, is applied to structures moving, but also to circuits in electrical engineering. So you get fascinated by the math and seeing why and what kind of factors influence how a building resists.
Yeah.
And because of that, I decided to take the wind engineering course in the master's, and also other courses due to earthquake. So I was still sitting on the fence for both.
Yeah.
They were both very interesting. So I did an exchange experience in Istanbul. So there was the exchange program funded by the European Union called Erasmus. I did a little bit of earthquake engineering courses, like structural monitoring, and a little more in depth about, applied research in earthquakes. And that was really fascinating, and especially like, Turkey, because a lot of earthquakes also,
right. They had a lot of devastating earthquakes.
Exactly,
yes.
even recently. So that was very impactful to me. Then when I went back, at the conclusion of my exchange experience, I took the wind engineering course and saw the scale of these events, starting with the Tacoma Narrows Bridge, which is a very famous video. I invite anybody who is interested in the possible effects of wind,
Yes.
how they can make a very sturdy bridge just get mangled. And that was really due to a phenomenon that was not understood at the time even. And here we're talking about like the early 40s, so not a very long time ago. And earthquake engineering is really progressing, and as we speak, there's a huge community in science that does research in earthquake, and that's one of the reasons IBHS also, is mainly involved in the perils that we do, which are wind, hail, wildfire, and wind-driven. So based on that, I felt more the motivation to actually dive into those wind effects that yet need to be understood. As we speak, there are some phenomena that are still being studied. And that drove me, to choose. At some point, you have to choose.
Right. Like, which path do you want? You're like, I don't know.
Exactly. So I had to choose, and I went with wind engineering, and particularly in Genova, a lot of floodings happened in the Adriatic, North Adriatic, because of thunderstorms.
Yes.
A high gust of wind that caused damage at ports. I remember I was coming back from class one time, and ironically, the professor was teaching us hydrology at the time. It was raining intensely, and he was telling us, well, now you see like a lot of rain, and theoretically, there should be absorption, and everything gets drained towards the river at some point. I walked out, and as soon as I got to the train station, the whole city was flooded.
Wow, yeah.
So, and that was shocking to me as like, a thunderstorm that you usually see on the Weather Channel and something happening.
Right.
You wouldn't expect it to cause this much of damage with all the infrastructure that we have. So that drove me actually to want to study the wind-related effects of thunderstorms, especially with the damage they cause, starting from the early 60s on aircraft and whatnot until now. And that's what drove me to go for my master's exchange for my thesis at RPI in upstate New York through my who was my mentor at the time, who sparked that interest.
Yeah, and it's great to see how these experiences that we have, where weather is impacting our built environment, right? That's all that we do here at IBHS, right? We do that across multiple perils, and we're going to kind of focus on wind today. Well, actually wind and wind-driven rain, which we haven't talked a lot about wind-driven rain, and a lot of people might not really think about it. They probably just think, oh, it's wind-blown rain, and it's just, it's not going to, if you've got an umbrella, it's not going to do a whole lot of good when there's wind-driven rain, so it's one of those things that's probably just more like a nuisance, but it actually is a fairly big loss driver here, and it's one of these things we call a loss amplifier. And so we'll get into kind of why we care so much about that particular side of the peril. But now that you're here at IBHS, you have your PhD now. We're full into our wind research and now wind-driven rain research. I kind of alluded to this when we started that we also do field deployments here, and you got to go on your first one over this past summer. As I mentioned, we do these post-disaster investigations where we actually go in after an event, and we do that from a research perspective to try and see what knowledge can we gain from the field and say, okay, what were some of the failures here? What were some of the successes? And if we can then observe those things in the field, that helps to inform our research here. And we've talked about our HAIL program before with Dr. Ian Giamenko, who's been on here a couple times. So that was the team that you got to go out and experience some time with. Tell us what that was like.
Oh, yeah. So that was a thrill.
Yeah.
Just in one word, a thrill. And it's because the objective of actually trying to deploy the probes, and I'm sure probably talked in detail about it, but we are on an actively trying to predict a small-scale severe convective storm in real time, and where we need to deploy these probes to get the measurements that we need actually as real data. So, like within the matter of half an hour, things can change, and you need to drive a long distance just to position yourself and try to capture that. And it's all totally worth it, like, putting the sweat when you look at that data and see that you actually got something that you can analyze and replicate here at the lab. So yeah, we deployed for about 18 days. We spent about a week in the Texas Panhandle. And
very familiar with that area.
Yes. It was storms back and forth. I think from what I remember, we likely did not deploy more than twice in a day, and by deploy I mean like go actually ahead of the storm and position.
Yeah, that's something people don't think about. It's like we can deploy, but then we have to go get the instruments and then do our measurements. And so in order to be able to do that, you got to be really quick on the draw. So it can be a fast-paced couple of hours.
Exactly. Additionally to that, this time we had for the first time asphalt shingle panels.
That's
because
right.
We wanted to look at the actual real damage caused by hail when it's outside, like on a roof, how it would look like on one of our panels, and compare that with the results from our testing here at IBHS. Right. So taking panels out from a van and putting them back on, that also adds some time. So we tried as much as we can to be accurate in our prediction, and that adds also to the stress of making the right decision on the go. So yeah, and we went then to Oklahoma and what we call no man's land.
Yes,
I learned that.
There are a few areas, if you've ever been out to the plains, it is beautiful countryside, but sometimes there's a lot of nothing, and then there are towns, and that's where you kind of refuel and everything, but there's a lot of open space to cover.
Beautiful. And that was the first time for me going in those areas and finding the storms, how severe they can be.
Yes.
That was shocking to me. Like I have experienced for the first time, like seeing an actual mesocyclone dropping hail, and then you realize the severity of, and you understand more like why do we do these things? Because as a large-sized hail can cause significant damage, and we really need to see how we can actually rate whatever we put on our roof and develop an actual performance rating that is realistic. And it's all about being realistic. And we will revisit that also on different perils.
Right.
But yeah, was thrilled, and I'm happy to do this again because as a scientist, we are always, and for anybody, like the curiosity, I think, is a fascinating thing about.
Yeah, and I agree with you there. Having done my first real storm chasing trip with our department when I was in graduate school at Texas Tech, being able to just see a supercell for the first time I believe we were in Southwest Oklahoma. Some colleagues of mine at the time were like, hey, our classes, they canceled this class this afternoon. We don't have any labs today that we're teaching. So anybody want to go anybody want to go chase some storms? We're like, okay, I'll go. But getting out there in the plains didn't produce a tornado. We didn't get into the core or anything or experience the precipitation from it. But it was just out in an open field, and just to see how large these supercell thunderstorms, the mesocyclone that you referred to, how expansive they can be, and they can produce some really gnarly weather that if you have never, here in the southeast, you've now experienced severe thunderstorms here in the southeast. They can be pretty rough and tumble.
Yes.
But even still, and I've grown up here as well, but even still, getting out into the plains, they are just a different type. They're a different beast, and you really see the hazards that they can bring. Just torrential, heavy rain, varying sizes of hail, some of that large, and we know even small hail can be damaging in the aggregate. We've done that research here. But the amount of rainfall, and then wind and rain, right? Wind-driven rain that we get in there. Wind-driven rain is something that we deal with across all perils, but it is fascinating to get out there and observe it in the real world, and that does help inform the work that we do here. And even what you said about the asphalt shingle panels that we're deploying, we're also deploying those right next to our disdrometers because they're collecting that data about the hail, right? And what's the one-to-one? So yeah, that's really what we care about.
Yeah. So exactly, we were collecting all all the metadata that we can collect to actually replicate everything. So the visual of the damage, the characteristics of the hailstones, the mass, size, shape, and we crush them to get the compressive strength, just so we can take everything and do it here, knowing that, all right, if we do this kind of test with this given size of hail, this is the type of damage that, give or take, we need to expect.
Right.
Just to always validate whatever experiment we do.
And that expectation of performance, right? You kind of mentioned that is the thread that kind of follows everything we're going to talk about today. That's ultimately what drives a lot of our work here, is that when we do these tests, it's ultimately we're kind of taking those current test standards that are out there and seeing, are they valuable? Do they tell us what we need to know? Because that's how we know what to expect from them. And to your point, asphalt shingles, we're learning maybe we shouldn't expect a whole lot depending on their age and that kind of thing. But it's all a part of the process. So we've covered the hail side of deployments. Now you've had that, but you got to go on another deployment this past fall. And so in late August, some of you listeners may remember, we had Hurricane Idalia that maxed out as a Category 4 hurricane with 130-mile-per-hour winds. Thankfully, it was weakening as it approached the Florida coast, the Big Bend of Florida, which we know is a very vulnerable area for storm surge. And while we don't research the impacts of water here at IBHS, we do know that it is one of the deadliest aspects of a hurricane, of a tropical cyclone, is water, whether that be storm surge or freshwater flooding from rainfall and the like. So we do care about those threats, but we just don't actually research those here. But yeah, it did make landfall as a Category 3, so it was weakening upon landfall at least. But there were some interesting observations that we'll get into a little bit. Let's just jump into them really quick, and we'll talk a little bit more about some of the observations that you got here in a minute. But Idalia, while it was powerful in winds when it maxed out there, this was different than, say, a Hurricane Ian, right? Where much larger storm, a much larger wind field, right? What were some of the characteristics of Idalia that we saw?
So based on the measurements and the measurements that we collected from our IBHS tower at 10-meter height, I remember I was comparing the data we got with some of the models that they were looking and plotting the swath of the wind field. From the measurement, what was surprising to me is the 3-second gust speed at 10-meter height close to the eye of the hurricane was quite lower than what was predicted. And the particular thing about this hurricane itself was the strong gradient of wind. So as you move out further of the eye of the hurricane, there was this sharp drop in the wind speeds. And this is not something that you typically observe. And this kind of data actually helps correcting or feeding into whatever data you have to improve your prediction. So, but just to add, like the wind speed was one aspect, but like we went there and measured also temperature, pressure, and something novel. But yeah.
Oh, well, yeah. So you were kind of getting into some of the variables there that we're measuring. Tell us a little bit about this tower. So it's a PIP tower, which stands for, what was it? I wrote Precipitation Imaging Probe.
Yes.
I had not heard of one of those. I'm a meteorologist, but that was not my field of study when it comes to tropical cyclones and that kind of thing at Texas Tech. We did have some deployable towers that I think are similar. I didn't personally work with those, but I know our colleagues did. But tell us a little bit about this tower and what it is. What's it measuring?
Yeah, so thanks to our collaboration with many entities that do research, including University of Florida. University of Florida is very active on hurricane deployments. They have their own deployable towers that are trailers that are about 10,000 pounds that you tow, and yeah, they're pretty heavy, especially when you have them on a truck and driving them. And what they do is they measure wind speeds, pressure, temperature, and particularly the wind speed. They measure at 5 and 10 meters. One of them measures also at 15-meter height. And we did leverage that connection with the University of Florida also to have a fourth tower. And while this tower is very similar to the ones they have, they measure wind speed also at 5 and 10-meter height and pressure and temperature. We added something that is yet to be explored in science. And to your point, the Precipitation Imaging Probe, the PIP, what this instrument does is it measures the size of the water droplets and it counts them. So by doing that, we actually, while we are measuring the wind speed at the same instant of time, that PIP detects, counts, and sizes the water particle droplets.
Okay, so drop size, yeah, gotcha.
Exactly. So this is something that was done only one time, and that was in Hurricane Ike in 2008.
Yes.
And it didn't move forward afterwards, and who knows why.
Yeah.
So we are navigating here a new zone, exploring. It's like, that moment when you get something for the first time, and you're like, wow, okay. What are we going to do now?
Yeah, you're like, well, what do we do with it? It's new.
Yes.
And that's cool that you pointed on that, right? We talk a lot about here at the lab, we're doing things all the time, right? We're using things that, we might look at an object and be like, okay, this is what its purpose is, but like, how else can we use it here? So we do our own kind of prototypes, designs, and sometimes we 3D print things. We're like, you know what, this doesn't exist, we can't buy it anywhere, so let's just make our own. So it's kind of that ideation and creativity and fabrication and innovation really that takes place here. And to your point, this imaging probe, the precipitation imaging probe, we're able to do something that, right, it's maybe only been one other time that this kind of data was really collected. So this is kind of among the first of its kind type of observations. And I mean, what's it feel like to be a part of an initiative like that?
So it has many layers because I also experienced a hurricane event for the first time.
Right,
so,
yeah.
Having to driving, and I decided to go using my car because I didn't feel comfortable renting a car.
Do you mind if I take this into a hurricane? Which, just to let you know, universities do all the time, so they kind of know that you're coming. So that's when your contracts with them get a little bit particular. So
exactly. So and then University of Florida gave the go for their deployment. So we decided, and we want to help and we want to be there also.
Right.
The decision was made on the day before, 2 days before. So the hurricane, I think the landfall was Wednesday morning. Monday morning was the decision made, like 48 hours before landfall, give or take. Then I went down to Florida, and by midnight I was there. Tuesday morning, so the day before the hurricane, about 24 hours, I was at UF at the Powell Lab, equipping and getting getting the towers ready and really helping because I really had not much experience and I didn't know much how to use the towers, and it was thanks to our collaborators at University of Florida who
that's
had
great.
me. So we left the campus at about 10 in the morning, and we started looking at the National Hurricane Center updates because a good thing about the hurricane is that you can actually now predict its trajectory, give or take. So
the
we're
track
getting
forecasts are great.
right. So now we've come way more accurate than a few decades ago, at least predicting the trajectory. So as the National Hurricane Center was posting updates, we were making decisions based on that, where to deploy a tower or two. So we made a decision to deploy 2 towers around the Gainesville area, one to the south and one outside the water waste management facility in Newberry, so a little to the southwest of Gainesville. And that was done by about 1 p.m., give or take. So we were trying to deploy 1 tower after every update. So this way, as the prediction became more accurate, we make a better decision on when to deploy, where to deploy the next tower.
And so as you're thinking about where to deploy, what are the variables that you're looking at? Are you trying to get close to the eye wall or the center of the storm, or just where you think some of the heaviest rainfall is going to be?
Yeah, and that's a very good question because there are a few factors. So for example, for the PIP, we want it to be as close as possible to the shoreline. Because as soon as the hurricane starts dissipating, we wanted to get the rainfall rate, or like what the rainfall looks like using the PIP. The other factors are the towers need to be in open terrain configuration. So basically a flat ground with least vegetation possible, so no trees. And no power lines also, because you never know what might fall or what objects might
Absolutely. When
fly
there's wind
around.
involved, you definitely have to do sort of a sight scope and be like, this is no good, or like, this can work, because you want that instrument to have that full visibility of the elements, right? So that those measurements can be really solid.
Exactly. As you mentioned, and to your point also, the open terrain configuration is a very good in wind engineering as a reference, because the wind speeds usually are also measured, on the runways at the airport. So that's kind of the configuration that we want. Besides also all the fact that we need to avoid all the windborne debris. So it makes our life easier as a scientist to convert, but also for safety purposes, definitely. So this is like the perfect condition when we find it. It's not easy.
Oh yeah,
because,
I imagine not.
Yeah, especially when you have a lot of, buildings, if you're like close to a city or a rural area. So that actually takes some time. But also another factor that is very important is we need to account for the fact that if there's going to be any storm surge, what is going to be the expected wave height, or like, the water height? And we need to make sure that when we put a tower that we can actually come back and retrieve it. And we don't want it to be pushed by water anymore. So that was a very important factor that actually Ian, thanks to Ian, he was trying to give us insight on the go also to avoid this area, Keaton Beach, for example. He like showed us what the where the water is expected to reach in terms of waves. So we tried avoiding those areas.
Yeah, that as I mentioned earlier, the storm surge, from that perspective, this is again one of the most vulnerable areas to storm surge in the continental United States. There's that southwest coast of Florida, which was hit by Ian last year, and then also the Big Bend. And so, it is very important to know where that surge is going to go. And I know that Ian, in his time at Texas Tech on the hurricane deployment team, that's definitely something they had to deal with. And sometimes you ended up having to wade in some water to go get the probe, because you can't just leave it out there. It has very valuable data, and the instrument itself is valuable to you. We don't just have thousands and thousands of dollars to keep recreating instruments that we just go get damaged in a thunderstorm, or in a hurricane. So it's very important to, like you said, you want to get close to the coast, but at the same time, you have to be, how close is too close, and so that we still get what we want, but we don't jeopardize the instrument or jeopardize ourselves and from a safety perspective.
Exactly. I mean, the towers are engineered. Like there's a company that actually designed them. they were tested with wind speeds and other standard engineering practice to make sure that it does not fail for any reason, because this involves a lot of effort when you actually take it out and put it there, from the instrumentation to all the infrastructure that you make to the people taking some margin of risk on making decisions. We need that data and we need the instruments. So yes, we were trying to be very careful, like as we were mentioning earlier, considering all the possible factors. And then as soon as we left those towers, we went back. So like the whole tower deployment thing actually ended around 3 a.m. And so like a few hours
Late
before,
night.
yes, we tried using as many National Hurricane Center updates as possible to make sure that we install those instruments where we know we are gonna get information that's gonna be useful for us. And then we drove back to Gainesville and stayed, took shelter until the following day. I have to say that the hurricane experience itself it was overwhelming. Because when you go there before the storm, you go like to a store to buy supplies or there's a rationing of water, and I experienced it for the first time, and even now, like as I'm learning on the go, I'm even more motivated to go on these events for these particular missions, because this saves a lot of trouble on the long term for families, for businesses, for everything.
Yeah, you're right, and that's why from my former life as a broadcast meteorologist, we're constantly preaching over storm season. We even say that here at IBHS. Have a plan, right? Have those supplies, like have your go kit, and if you live in these hurricane-prone areas, this is something. It's a way of life every year. You could anticipate that every single year. There are millions of people who may never experience a tornado or something like that, but then they're here along the coast, especially a place like this. There are millions of people who might experience a hurricane every other year or at some point in their lives. So kind of knowing all of the planning that goes into that, and we're just trying to get in there and collect data. We're not trying to also live in there. So it's just that's why we talk about that preparedness. Obviously, we do that from a structural perspective, right? We want your home to be prepared, but on the personal level too, you have to have things like food and water and that kind of thing to last for a few days if the power is out. It's an inconvenience, but you have to prepare for that.
Yeah, so exactly. And as someone who does research in these fields, I acted basically or essentially as I was someone who was resident there in Florida.
Right.
I went to grab water, I went to grab canned food and beef jerky. And I even had cash because that was the recommendation. You never know. Exactly. And a flashlight, and I had my computer, and so and then I stayed in the hotel where I was residing in Gainesville until the storm was declared to be over. There was no threat anymore.
Well, that's great, and I'm glad that we got to kind of share what your first experience was, and really probably your first hurricane experience. So you've had a lot of cool firsts from the weather side this year. You got to experience a hail field deployment for the first time. Supercell thunderstorm. Now we've got a tropical cyclone. So, and you've already got earthquakes on your list. So you're racking them up. And technically, you've got wind-driven rain now from the hurricane. So you've only got to experience a hailstorm directly now.
It's an emotional roller coaster.
It is. Yeah. But that's great though, and it's cool. Like I'm a scientist, like kind of come through that as well, kind of remembering how I felt like experiencing these things for the first time. It just kind of really hits home, and we talk to people about that, like from a damage perspective. Once you go through a storm and you see how the damage can occur, you're like, oh wow, I didn't realize it could happen that fast. I didn't realize that's how wind damage occurs, or how water gets into my home, or how hail damages our shingles or our siding or that kind of thing. And that's the kind of thing that we want to use those experiences, and we bring you those visuals here from the lab to try and educate you so that you don't have to experience a loss like that from a property perspective. And we can try to give you some information on the front end to try and prevent that. So it's cool for us to experience that on our own, because that helps us be better communicators for you as well.
Exactly, and I have to say, when we were going to retrieve the towers on our way back to Perry, then you experience you see with your own eyes, the damage caused to not just the trees or power lines,
Right.
but also to buildings. Now, the Big Bend was lower in population than other areas,
Right.
but still you see like buildings that had no roof,
Yeah.
or an entire roof collapse on what's underneath. And that's sad when you see it for yourself. You see the magnitude of, or the importance of actually having an actual building code that does provide better performance recommendation for component, like down to the
Right.
components, not just. Now, gladly, the Florida Building Code is performing. We've seen the success from Hurricane Ian,
Yes.
and I'm sure many others have talked about this. But you still realize that we need to solve the problem down to the basic or smallest component, because one failure of a component can trigger a lot of internal damage.
Right.
If you have that component being damaged on the roof, there's going to be rain during a hurricane. You're going to end up with a puddle inside your, whether it's a house, whether it's a business.
Right.
You're going to have to deal with a lot of aftermath in terms of cleaning up and things like that. So a small component damage can amplify the internal damage.
You're right, and that's a great segue. You kind of like made that transition for me. It's like now we kind of opened it up that we're going to talk about Idalia and some wind-driven rain, and that's not something that people really think about. Oh, like when you have until you have a water claim, you don't really realize how much how easily it seems to get everywhere. Right? It's one thing to deal with, wind damaged part of my roof or damaged part of my siding, but then when you have water getting into the structure as well, that's something like what you just talked about, small component failure, then cause a cascade of other opportunities for damage, loss and costly insurance claims for you as a homeowner. So let's talk a little bit about rain now. You just kind of alluded to it, that we can get, if we have structural damage of some sort, then water can get into the home. Let's talk about rain from a perspective of how people see it, right? When a hurricane comes through, you're thinking about, okay, 5 to 8 inches of rain fell in this storm, but there are also other questions that we have to ask, and you alluded to it when you talked about the PIP, the probe there that's going to be measuring the drop sizes. Why do we care about drop sizes, right? Because we're thinking about how much rain falls overall, but we don't know how fast it falls. Why do we need to know what the drop sizes are?
And that's a very important question. Even though we collected this data for the first time, and we're seeing how we implement this in our research, but this is similar to, if we look at the other perils, any other peril, whether it's an earthquake, it all started with recording the earthquake using an accelerogram, recording that. With wind damage, recording the wind speed. Same thing goes to rain. We need to understand the anatomy of the peril itself, so we can understand how to realistically replicate that in a way that when we simulate this kind of event, the effect is something that you experience out there. Now, there are some standards at the current time, but the way they are applied to rate any window assembly or wall assembly is basically you just apply a static pressure with a certain wetting rate, which is like a nozzle that just sprays a certain flow. The question here that, well, first of all, from a wind perspective, we definitely know that wind outside is not just constant static,
Right.
So you have gusts, you have a lot of turbulence. So that's in terms of wind. Then from the other side is, well, how do we spray the water? Do we just throw a bucket of water?
Yeah.
Or is it going to be just mist, right? Even if we're doing the same wetting rate, we need to actually give an input of a realistic distribution of water droplet sizes, so we can simulate the realistic event. Then we can talk downstream and look at the effect. I remember I was chatting one time with you, and you used an analogy. It was like a house, basically, right? Like
exactly. It's like, if I'm standing outside my house and I take the water hose and I turn the little dial to mist, and let's say there's a little breeze, with those little water droplets, they just kind of like flow where the wind takes them. They just kind of meander, and then some of those might hit the side of the house, and then some of them might get deflected from the airflow and go somewhere else. But let's say we turn that hose on to a more direct spray, a lot of that water, it's just incident with the wall, right? It's just hitting the wall and it's going to run down. It's not flying all over the place and just going where it will. So this is why, how does this change from like a wind perspective, right? It's going to carry those drops differently and determine how much of that water actually hits the structure.
You hit the nail. I think you mentioned something very important, which is the inertia, the size of the droplet.
Yeah.
If you have something heavy, it's definitely going to be carried less in the wind field than something very light like mist. And that affects how this water distribution impacts the building. And based on how water accumulates on the surface of the building, there is a percentage that gets admitted through defects, cracks, or even seals. So by doing that, again, we can look into at least replicating that in our wind tunnel.
Yeah.
The same way that we replicate an actual wind field that we measure. Sometimes we measure a hurricane wind field and we generate the same exact thing because we want to be as accurate. And we do have theoretical studies in wind based on the measurements. So that's what we do. And now it's time to actually start doing that on the wind-driven rain side.
Right, right. And thinking about the rain side, we did a water intrusion demonstration here in the lab with my team a couple months back. We got to be in the house as we were videoing it. We cranked the winds up to about 50 plus miles per hour, I think, because from safety reasons, we can't be in there when the winds are much higher than that. So we're inside the structure videoing what's happening, and we had a set of French doors there that were facing the fans and the sprayers, right? Because we can spray wind in our spray water in our test chamber as the fans carry that water. But Ali, just the speed at which that water started pouring in, because the roof was damaged, so we had lost the shingle and underlayment cover over top of that. So we just had the roof decking, the OSB decking, but there were cracks there at that seam. That's something that we talk about here in our Fortified program. We have that sealed roof deck, which basically just, it tapes that seam and creates a watertight seal so that if a roof cover gets damaged, the decking, it's not leaking water into those cracks. But in a matter of 15 minutes, there was water everywhere. So from an insurance perspective and a loss perspective, this is why we care, right? Because water is just so damaging and it can inflate claims for thousands and thousands of dollars.
Exactly. I mean, if I want now to open this bottle of water,
right,
and just
just
spill
a
a
little demonstration.
Just like less than half a liter of water can cause a lot of mess inside to clean up. So imagine if actually your roof is letting water in. And the thing is, if you have, let's say, a hotel or a hospital that you are operating or managing, you're not just gonna be, like replacing, but you're gonna be shutting down, especially if you're like a critical infrastructure, you're gonna be shutting down any room dedicated to that service, because you're gonna have to be replacing the soffits, for example, or doing some work on refinishing the wall or removing the mold, which is way worse. In my opinion.
Yeah, the mold remediation, that can linger. I mean, I know after Hurricane Harvey, with all the flooding that they had, granted that was water from below from the heavy rainfall, but again, water, right, lasting impacts, and sometimes it can gut an entire home.
Exactly, and imagine with the wind, coupled with the wind, that might cause some damage also, that can trigger more cracks or openings or defects to let more water in, right?
Compounding.
Exactly. So, and to your point, this is why we have, one of the reasons we have the sealed roof deck with Fortified is we are assuming that asphalt shingles are not going to stay on the roof for other reasons. But based on that assumption, we go and put another defense line, which is having more tapes, having, having tapes, because there is no tapes in other configurations or designations, and making more considerations, for example, with Fortified silver on the openings even.
Yeah.
So we do look at that as components in a system, let's say, and I totally agree. water intrusion is a big beast,
Mm-hmm.
and it's coupled with wind, which is already a big beast.
Right, right. And yeah, and thinking about the places where water can get in, I mentioned the French doors that we had. I forget if they were specifically rated or not for wind. The doors themselves did not fail because of wind, and by fail, I mean that the two doors didn't bust open. But water absolutely got in, and it got in very fast. So it just shows you that like these are kinds of things that we care about, right? Like window, like entry through the window around the seals. This is why we talk about like caulking your windows and your doors where you have cracks where it's not supposed to have a gap, right? To protecting those seals so that water can't find its way in, because just like with all perils, it will find the weakest link in the structure. That's certainly with wind, and that water will find its way in. If you talk to anybody that's been through hurricanes with any number of years, I mean, they'll tell you the places where it normally comes in. So it's our job to identify those areas, which we have. We know like even PTAC units or these air conditioning units that sit on top of commercial buildings. Think about hotels, right? The air conditioners that are in there. We have incredible water entry into that. So that's a business continuity loss and a commercial claim as well from all of the water damage. You're thinking about gutting, 100 hotel rooms. That's not a small bill.
Precisely. Like I'm out of like you hit the nails like exactly as, and to your point. So through PTAC units, for example, we have done that, and we have seen through that and other assemblies of testing and other practices of standard testings that we try and replicate in our own way. And by our own way means like actually trying to implement something that's simulates some gustiness, wind gustiness.
Right.
And we have seen how water infiltrates through as you have a gustiness of wind that just pushes, and that's really intuitive. But just underline the fact that even if you don't have damage itself, water can in a way still find its way through some weak links, and the PTAC units is one of them if they are not placed in a certain way that is described by the standard. And what we're trying to do now is couple the wind gustiness with a realistic distribution of water and actually rate the wall assemblies, the windows, the PTAC units to something realistic that they might experience out there.
Yeah.
Which is a big challenge moving forward.
And that reminded me of something that you and I talked about. Let's say that, and I did want to get into a little bit of the things that you observed in Idalia. We talked about some of the winds that we observe, from a wind gradient as you go away from the center perspective. But I'm curious. I wanted to talk about how what the wind and drop sizes look like for that as well. But first, I want to ask, like, let's say that we have a series of large. Let's say that we have the wind flow constant, right? We've got a building in our test chamber, and we want to crank up the fans to let's say 50 miles per hour. What are we looking at from a small drop size versus a large drop size in how? Because you talked a little bit about the pressure, right? So that's wind that's going to be pushing against the wall, and that's then coupled with the water from that perspective, right? So I guess kind of like what from a small drop perspective, from a large drop perspective, what do you kind of anticipate? And this may be the things that we're trying to figure out too.
Yes, and if you asked me this question a month ago or a month and a half, I would have told you I don't know. I have no idea. But looking at the PIP data, what I've seen when I was processing them a little bit is that at around the landfall time or a little afterwards, so when the eye of the hurricane got really close to the tower, I was seeing an increase in the size of the droplets measured by the PIP up to about, give or take, 5 millimeters in size, which is classified as a large droplet size.
What are the sizes of drops roughly to be considered a small versus a large raindrop or water droplet, we'll say?
So let me think. I do not have the exact limit, but from what I remember is about 0.5 millimeter to 3 millimeters is considered you know, like a regular droplet size. Anything above would be typically a large droplet of water, and at some point it splits into. So anything larger than about 3 or 4 millimeters is considered like a really large droplet. And I remember, like, even before the hurricane, when we were like deploying the towers, it was intense rain, but the droplets even, I remember before, and did look a little bit at the data, and there were some large, like more than the usual, I guess. But then again, we don't know what is usual because
right, we
are
don't
measuring.
know. We're measuring this for the first time. Yeah.
But it's like, you know, when you're driving and there's a thunderstorm and you have these big droplets of water falling down on you. So this is what it looked like. And well, on the note of, you know, thunderstorms, and I think it would be also of interest at some point to start taking that tower, or at least a smaller version of it that is quickly deployable relative to what we have, because the one we have is a big beast for hurricanes. We might need something quicker for severe convective storm, but really look at how water also looks like in the event of straight line winds or doing a thunderstorm.
Yeah, thinking about like derechos, right? We just had the August 2020 derecho that was so intense there in Iowa, an extended period of significant straight line winds, 60, 70 mile per hour plus. I mean, I know it got up over 100 in some of those areas, but it's a shorter duration than a tropical cyclone, right? So it's kind of like, how do all these perils differ from a wind and water perspective? Because that's ultimately going to help us, you know, inform insurers, inform test standards about what to expect. It goes back to that expectation of performance of my materials, right? If I've got a French door, it's like, is how we're rating them good enough, right? And I think these are some of the answers that you're trying to get to ultimately.
Yeah, because this takes us to the question that is the water droplet size distribution during a hurricane similar to something that might happen during a thunderstorm? Because if it is, then all right, we can make probably one kind of standard testing. If not, then we might need a few of them to simulate the different wind-related perils that generate water.
Yeah, and so it's like we said, if we can't observe it, we can't model it, all right? If we can't model it, we can't predict it. So it kind of all ties in, and when we go out into the field and collect these kinds of observations, in this case, you know, some that are among the first of its kind, you know, we'll start to figure out, you know, some of the questions that we're trying to answer. We might be able to answer those, but you said it so beautifully in the beginning that in your early work, you said, well, I finished my work and then I finished it with a question. And then I was like, well, now I have to answer that question. And that's oftentimes how the research goes here, right? We might solve one problem, but then we observed something else in the meantime that then sparks another area of research. So on that note, I mean, based on kind of what you've seen thus far in that data, kind of what are some of the next steps that you're hoping to take with this work? And I know we're doing this kind of an extension of some work that another colleague of ours here, Cora, has been working on with the cyclone test stations. Anything you want to share about that? I think you guys were just talking about this morning.
Yes. Well, as a matter of fact, Cora and I were scratching our heads this morning to try and answer some of what you asked.
A good conversation between two scientists over coffee is like, well, it's like, well, that doesn't make sense. Why would it do that? It's so weird. But these are the kind of cool, like, off-the-side conversations that we get to just kind of peek into. And Cora Pekal, he's one of our newest researchers here at the lab. So yeah, what was that little conversation about?
Well, so some of the conversation actually was, with the cyclone testing station in Australia and through Cora, there were some tests using the actual standard testing, whether it's ASTM or the Australian standard testing, to look at the wetting rates and the water intrusion rates given a certain wetting rate with a certain pressure to simulate like the wind action. But
right, how it's forcing the water through those openings, right?
Exactly.
It's like that's the pressure, right? You just think about like a water hose, right? You put your hand over it, you increase the pressure, the water shoots out really fast. So that's kind of like what we're thinking about, yeah.
Exactly, and from the previous phases of testing, actually, this is what they have seen. And applying constant pressure gives you a certain result, but then if you apply some gustiness, you will have a different result. So that is one. The second one is actually the pressures that are being applied, and that's actually from the conversations with Cora today, yesterday, and over the last period of time, is the pressures that are applied or the actual wetting rate are corresponding to high values that they need to be looked into again. So for example, the pressure corresponds to about 70 meters per second, which is kind of a design exactly design level event, but still we see water coming in at lower wind speeds, right? So the question is, how do we make a realistic box to test? And this is where they are right now at the cyclone test station. According to Cora, they are designing now an actual box that generates maybe a little bit of gustiness, and this is based on some continuation of the previous testing that Cora was doing, and to actually produce to put some different nozzles that spray water at a specific rate. And we ended at the same question: how do we how do we include this water droplet distribution?
Right.
And yes, this is the moment where we actually are, the ideas are starting to brew, let's say.
Yeah.
Hopefully we get a stew at some point. But,
yeah, no, that's great. And as we kind of move forward in this, I mean, it would be great to have you back on again to kind of talk about some of the ways that we've furthered some of this work. But I think in this episode we've kind of gotten to see a little bit about the creative process that goes into looking into new areas of research. Also, using some of the old tools and new tools, right? With our observing tower, how we can kind of be there on that next forefront of observational science, because that does feed into the work that we do here in the test chamber. Because if we can come and replicate those in the lab, that's one of the beauties of our chamber, right? Is that we can do testing at full scale with full scale structures, crank up those winds, apply the correct wetting rate, and get a more accurate depiction of how the water is getting in, why it's getting in, where it's getting in, and improve those test standards, because it's that repeatable method that we can do here that gives you that sample size to really say something about it. And so I thank you for sharing your work that you've done up to this point, and kind of like opening people's eyes maybe as to like, here's why you care about wind-driven rain, like, right, and the droplets. And as we get to observe more and more of these types of events, whether they be hurricanes, severe convective storms, or just maybe a heavy flooding rainfall, something like that, that's going to tell us a little bit more about the phenomena, like what is an average drop size distribution in tropical cyclones, and why do we care, right? We know now why we need to know these things, but it's just so many different questions right now that we've developed.
Exactly, and again, like I take us to understanding the peril itself in order to understand the weight, not just the weight X, the effect that it causes, similar to anything. If we don't have information about earthquakes or like the accelegrams, it would be really tough to actually.
Right.
It would have been really tough to solve the problem, or at least try to. Same thing for wind. And now what we're doing, we're pushing the needle a little bit forward on wind, and that takes us to why we go on deployments for all kind of perils that we are heavily or mainly involved in. We take what we observe, what we measure, and we use the full-scale tunnel that we have to its potential to actually simulate reality. And we actively look at the performance of the components in a real wind field. And that's the opportunity, and that's one of the reasons I really joined IBHS. It's really, you don't need to scale down your building, which really works looking at several aspects, like the aerodynamics, etc. To some extent, because in the end, if you're scaling down your model, you're not going to have a garage door, for example. You're not going to have asphalt
exactly. Those are real world things that fail all the time.
Exactly, which are related to which have their own issues, and that we also observed. So that was, there were some key aspects about the wind side. This is what we're hoping to get somewhere on using those data in the tunnel for rain simulation.
Yeah, well, that's great, Ali, and I think you've ended it nicely there, kind of circling everything back and as to why all these observations matter. I think you've gotten to see some of that curiosity when you were younger kind of all come to fruition now here at the lab. So we're looking forward to all the cool research that you'll get to participate in. And I'll be anxious to hear about your next field deployment whenever that is. We're going into the winter season, so might not be some opportunities, but we'll get back in the mix.
Yes, let's say that I'm fully trained now well, without putting the wildfires aside.
Yes. Maybe we'll leave the wildfires to our wildfire researchers there. So. All right, well, Ali, thank you so much for joining us today. This has been really enlightening and cool to just talk about your experiences on these field deployments, why we do them, and to learn, hopefully our viewers learned a little bit about wind-driven rain. It's kind of it's the peril that's on our patches, but it's just one of those things that haven't gotten to really talk a lot about in all the other work that I've been involved in here, but this has been educational for me as well, so thank you.
Oh, thank you for this experience. This was amazing.
All right, well, we'll have to have you back again soon to talk about your next deployment. Until then, we'll hope you'll join us for the next episode, and thanks so much for listening today. We'll see you for the next episode of the Disaster Discussions podcast.